All right, welcome to eCampus. So today we are going to revise conditional probability and some of the associated topics, including exams of probability, Venn diagrams, tree diagrams, and addition rules. We are going to be solving some questions. All right, so suppose that in a certain school, the probability that a student plays soccer is 0.18, and the probability that a student plays tennis is 0.25. Further, the probability that a student plays both soccer and tennis is 0.11. Now we have to find the probability that a student plays either or both of these sports. All right. So with this question, and as with any other probability related question, the first step almost 100% of the time would be to define your events. So in this case, one of the event would be that a student chosen at random and he or she plays soccer. So we're going to call that event S, and where the student plays soccer. And we also know its probability, that probability of S is 0.18. Secondly, we also know that the probability that a student plays tennis, so we call that, let's say, event T. And its probability, we also know the probability 0.25. Further, we also know that the probability that a student plays both soccer and tennis. Now that's basically intersection of the two events, right? Because we are looking for a student who plays both soccer and tennis. So for an event where a student chosen at random and he plays soccer as well as tennis. So that is probability of S intersection T, right? And that is 0.11. We should also have a look at this above scenario using a Venn diagram. So let's say this is my sample space. This is my event S. And since there is a non-zero intersection, so I should be looking for some overlapping, right? So let's say this is the event S. So let's say this is another event, that is my T here. So I have some overlapping region, and the only reason I do have this overlapping region because there is a non-zero intersection, right? So let's use some colors to depict it properly. All right. So let's say this is my event S, and this is event T. Right. So overlapping region, you see this black region over here. This is basically probability of S intersection T, right? And if we were to be looking at the overall union, which is basically what we need to find out, that the probability that a student plays either or both of these sports. So this black region is basically both of these sports, and individual red and green gives us information about either of these sports. That's basically union. So we can also see this from this Venn diagram, then that these three additions, that these three colors individually gives us the overall information about the union. So we can also use the addition rule alternatively for finding this probability. So probability of S union T is nothing but the addition of their respective probabilities, probability of S plus probability of T minus the probability of S intersection T. This is our very own, very famous addition rule for probability. Now we know the individual probabilities. Probability of S is 0.18 plus probability of T is 0.25 minus the intersection, that is also given 0.11. So pretty straightforward. And this adds up to 0.32. So this is the probability that a student chosen at random plays either soccer or tennis or both, right? So that was a warm-up question. Let's move on to slightly more trickier question. All right. So in a certain town, the probability that it rains on any Monday is 0.21. And if it rains on Monday, then the probability that it rains on Tuesday is 0.83. Whereas if it does not rain on Monday, then the probability of raining on Tuesday is 0.3. And we have to find the probability that for any given week that it rains on both Monday and Tuesday and on Tuesday only. All right. All right, for this question, this looks like a question where the occurrence of one event, which in our case, raining on Tuesday, is dependent on whether it rains on Monday or not. So this is the classical example of a conditional probability, right? So for conditional probability, like after designating or defining your events, the next step should be to uh, draw a tree diagram. That helps a lot. So for our case, let's call the event M and T. And M for any given day, whether it rains on Monday and rains on Tuesday. And since we involve that whether it rains or it does not rain on Monday, so we also gonna define their complementary events as well. This is does not rain on Monday, and T complement is when it does not rain on Tuesday, right? So after defining the events, next step is to draw a tree diagram. And I would recommend 100% of the time when there is a question related to conditional probability or when there are cascaded events, events that are aligned in cascade or in series, right? It's always recommended to draw a tree diagram. And for a tree diagram, I always start with the triggering event, right? So our triggering event is whether it rains on Monday or not. So accordingly, it rains Monday or it does not rain on Monday. All right. So we know the probability of raining on Monday, it's 0.21. And since that's the complementary event, so it does not rain on Monday is nothing but 1 minus 0.21 or 0.79. Afterwards, if it rains on Monday, then the probability that it rains on Tuesday is 0.83. So probability that it rains on Tuesday, given that it has rained on Monday, is 0.83. And on the very same footings as we did for the complementary events, we can define the probability that it does not rain on Monday. Sorry, the probability that it does not rain on Tuesday, given that it has rained on Monday, is 1 minus 0.83, this thing. So 1 minus 0.83 is 0.17. And for the case when it does not rain on Monday, this one, the probability of raining on Tuesday, given that it has not rained on Monday, is has been given to us. That is 0.3. And for the complementary event, the probability that it does not rain on Tuesday, given that it has not rained on Monday as well, that is 1 minus 0.3, right? So that is 0.7. So we have a well-defined tree diagram here. So this is our first event here, whether it rains on Monday or not. And then this here is our second event, which is dependent on whether it had rained on Monday or not rained on Monday, right? It's also beneficial to mention here, and I'm going to write in red here, that the product of these two probabilities gives us the intersection. And also we call that the multiplication rule of probability. So this is nothing but probability of T intersection M, right? And this one is nothing but probability of T dash or T complement intersection M. And similarly for the rest two as well. For example, this one is probability of T complement intersection M complement, right? So based on that, now it is quite easier. We have drawn the tree diagram, we have defined the events. Now let's try to find the probabilities. So for part A, we have to find the probability that it rains on both Monday and Tuesday. All right. So we have to find this probability that it rains on Monday and Tuesday. So we have already mentioned it alongside that this is the probability of T intersection, and that is the probability of it rains on Monday and probability that it rains on Tuesday. So this is an and event where we are looking for the event where it rains on both days. All right. So this, if you were to look at from the branch itself, you see this is this branch, right? So probability of M intersection T is nothing. But by the way, this follows the commutative law. So probability of M intersection T is equal to probability of T intersection M. So there is nothing to be confused about here. So this is equal to probability of M multiplied by the probability of T intersection M. All right. So probability of M is 0.21 multiplied by 0.83. Very quickly, the answer comes out at 0.1743. And we can round that off to three significant figure, that is 0.17. Moving on, we also need to find the probability that when it rains on Tuesday. So we need to find this probability when it rains on Tuesday. So if we look at this diagram above, and let me highlight the branches when it rains on Tuesday only. So if we have a look at real quick. So for this event, it rains on Tuesday. And if we look at the other three branches in this event as well, sorry, in this branch as well, it rains on Tuesday. So there are two possible options when it rains on Tuesday, either when it rains on Monday and or when it does not rain on Monday. So probability of raining on Tuesday is nothing but the sum or the addition of these two individual probabilities. So let us write that down. Probability of T is equal to probability of T intersection M plus the probability of T intersection M dash. So we also know these individual probabilities. So T intersection M, we just find in the previous part, that is 0.17 plus this thing is 0.3 multiplied by 0.79. So our answer comes out as 0.41. All right, so far so good. That's the end of the second question. Let's move on to another question. Here we will be looking at the tree diagrams in a little bit more detail. All right, so let's have a go. Box A contains two red balls and a white ball, and box B contains one white ball and a red ball. So a coin is tossed. If tail appears, two balls are drawn without replacement from box B, where box B contains one white ball and a red ball. All right. And for the other case, if head appears, two balls are drawn without replacement from box A, and box A contains two red balls and a white ball. All right. So there are two boxes with respective colored balls, red and white. Uh, and the triggering event here is a coin toss. So again, this is an example of cascaded events and the conditional probability. So our events start with a coin toss, and based on if it is a head or a tail, we go to a respective box and choose certain number of balls, right? So for part A, we have to draw a tree diagram. And another important thing to note here is that we are doing it without replacement. So without replacement means that whenever we draw a ball, we keep it to the side. We does not just to place it back into the bag again. All right. So that's an important detail, and that significantly it can significantly alter the course of action of your solution. All right, so let's start with the tree diagram. But prior to that, let's first define the events. So since the names are quite straightforward here, let's stick to the names as the event names. So for example, box A be the event when we chose box A, right? And similarly for box B, be the event when we chose box B. And for the head and tails, let's stick to the names, right? So let's start the triggering event. So it can either be a head or it can be a tail. right? In case of tail, two balls are drawn without replacement from box B. And box B contains only two balls, one red ball and a white ball. So uh, in case of tail, we have two attempts, like first attempt, we can call first attempt and second attempt. So we have to draw two balls. First attempt means that we are drawing the first ball, and second attempt means we are drawing the second ball. And remember, it's without replacement. So box B contains one red ball. So for example, first case would be that the first attempt we draw a red ball, and or the other case could be that we draw a white ball, right? And since we are doing it without replacement, in the second attempt, there could be only one option left. If it was red in the first attempt, in the second attempt, it could only be a white one, right? And here it will only be a red one. So that's pretty much it. So there were only two balls in box B. So there were only two balls in box B. And if it we chose the red one in the first attempt, the only ball left would be white, or the other way around. It could be on the only ball left could be the red one. All right, so that's pretty much it. That's the whole scenario for box B. For the case of head, we have to choose again two balls. So there will be two attempts, first attempt and second attempt. But we have to do this from box A without replacement again. But box A contains two red balls and a white ball. So let's say we call two red balls at red 1, red 2, and white. Right? So this is box A. So for first attempt, there can be three possible scenarios. Either it's a red 1 or red 2 or white ball, right? So this can be red 1, red 2, or white ball. Since we are doing it without replacement, if we chose red 1 or the first red ball, then we have two possible choices in our second attempt, and that could be either red 2 or the white ball, right? And I think we are cramped up about space a little bit. Let's insert some space here. All right. So for red 2, the options could be that we have red 1 or white ball. And for the white ball here, if we choose white ball in our first attempt, then in the second attempt, it could be first red ball or the second red ball. So this is, although slide looks slightly complicated, but if you understand the question fully, so this is a very straightforward tree diagram. So for the head case, we go to box A. In box A, there are three balls, two red and a white, and we have to draw two balls without replacement. So in first case, it could be any one of the three balls, red, first red, second red, or the white ball. And in any of the respective cases, since we are doing it without replacement, the other two options could be listed there, right? So this is a comprehensive tree diagram for the whole scenario. Now, based on this tree diagram, we have to answer a number of probabilities. So if each outcome is equally likely, that means the relative frequency of occurrence of each of the event is equal, find the probability that exactly two red balls are chosen. Now, if we go to the above tree diagram and find the branches where two red balls are chosen, we see this is one case, this is another case, and that's pretty much it. So there are two cases out of a total eight cases, or out of a total eight branches where exactly two red balls are chosen. So the probability that exactly two red balls are chosen, we can call that event as like maybe R2. The probability of R2 is 2 over 8. And this comes from the definition of relative frequency. The numerator is the number of favorable outcomes, and the denominator is the total number of outcomes. The total number of outcomes could be 8 in these possible combinations, and the favorable combinations are these two highlighted ones, right? So 2 over 8 is the right answer. For the second part, we have to find the probability that exactly one white ball is chosen. So again, let's go to the tree diagram that we drew above. So exactly one white ball is chosen. So we have to look at the branches and see where exactly one white ball is chosen in the respective branch. So this is one, this is another branch where one white ball is there. Similarly, this is one, this is another one, and we also see this is one branch, and this is another branch. All right, so these are the branches where there is exactly one white ball, where exactly one white ball is chosen. So if we can count these all, this is one, two, three, six total branches are there out of eight, or in more mathematical terms, there are six total outcomes out of eight where exactly one white ball is chosen. So let's say we call this event W. So probability of exactly one white ball is 6 over 8, right? Moving on to part C. All right, now we have to find the probability uh, part 3, where exactly two red balls are chosen given that box A was chosen. So now it is a conditional probability. So we have to find the probability that R2 the same as this one, but given that box A is chosen, right? So if you go above, this was the case for box A, and this was for box B. So when box A was chosen, uh, this branch and this branch were the one where exactly two red balls were chosen. However, when we are limiting ourselves to box A because of the condition probability, the total number of branches in this particular scenario, one, two, three, four, there are total six branches here, right? So we have counted the branches. However, we are limiting ourselves to box A only. Why? Because the question is that we have to find the probability of two red balls, and given that the box A was chosen. So this is nothing but equal to 2 over 6. Why 2? Because these are the uh, number of branches where exactly two red balls were there. And our total number of branches are reduced to 6 as opposed to 8 here in part 1, right? As there's a big difference because there was no conditional probability in part 1. We have to find the overall number of branches available, and then we chose, okay, there are two branches out of total eight where there are exactly two red balls. However, in part 3 here, we are limiting ourselves to box A only, right? Now moving on to part D. We have to find the probability that box A was chosen given that exactly one white ball was chosen. So we have to find the probability of box A given that only one white ball was chosen, right? So this apparently looks crooked because we are trying to find the probability of a previous event based on the occurrence of a later event. However, there is nothing to worry about. Let's go back to our tree diagram above. You see, the branches that are highlighted in green are those branches where at least one white ball is chosen. Oh, sorry, where exactly one white ball is chosen in the scenario. All right, but these are the overall branches, right? So our question is find the probability of choosing box A given that exactly one white ball is chosen, right? So our total number of outcomes are now limited to six, these green six, where exactly one white ball is chosen. Why? Because this is the given condition, right? We are limiting ourselves to now these green branches only. So given that these green branches are there, what is the probability of choosing box A? So you see 4 out of 6 green branches are from box A and 2 are from box B. So our answer is now limited to 4 over 6, right? So that was a good question. That was a good practice question. We delved quite deeper into the tree diagrams. All right, moving on to the one last question for this practice session. All right, so Chin either drives to work or takes a train to work. The probability that he is on time for work is 0.86. And the probability that he is late for work, given that he drives, is 0.3. And the probability that he is on time for work, given that he takes a train, is 0.9. So there are some conditional probabilities given, which I have highlighted in blue. And there is one a probability of on time also given, that is 0.86. So prior to moving on to the question, let's first define the events. So let's say, let me write here. Let's say on time be one event where chain is on time, right? In office, right? And train be the case, train be the event, sorry, when chain goes to office via train. And similarly, drive be the event when chain goes to office by driving. All right. So let's move to part A. Find the probability that he is on time for work given that he drives. So it's a conditional probability. We have to find this probability of on time given that he drives to work, right? Uh, Prior to solving it directly, let's first draw a tree diagram. Since we're going to be needing that in part B as well, let's draw it here actually. So the triggering event is whether he drives or takes a train. So he can either drive or he can take a train. We don't know the individual probability of either driving or taking a train, so let's keep it as it is. However, if he drives, then he can either be late or he can be on time, right? So late, given that he drives, or on time, given that he drives. However, these probabilities are known to us. The probability that he is late for work, given that he drives, is 0.3. And since late and on time are complementary events, if he is late 30% of the time, that means he is on time 70% of the time. So this is 1 minus 0.3. So this is 0.7, right? And similarly for when he takes a train. So he can be late given that he takes a train, or he can be on time given that he takes a train, right? So the probability that he is on time given that he takes a train is 0.9. And similarly, this would be 0.1. We don't know the probabilities of driving or taking a train, but it's given that he either drives to work or takes a train. So these are the like only two options that he can go to work. Like he either drives or takes a train. That's it. So these are complementary events. For example, if this probability is p, then this would be 1 minus p. So this would be helpful because there is only one variable that we need to find out, because of the information that these two are complementary events, right? So now let's, having drawn this tree diagram, now let's move back to part A. So we have to find the probability that he is on time for work, given that he drives to work. So we just draw the tree diagram here. So this is nothing but this particular probability, right? The probability of on time given that he drives, right? So this is equal to 0.7. We already found that out, but essentially, if you were to mention that in part A, then you could have said that this is equal to 1 minus probability of being late at office given that he drives, and that was 0.3. So this is 0.7. So that's for part A. Moving on to part B, find the probability that he drives to work. All right. So we know this particular portion of the probability. We know all four of them. But now we need to find the probability, and we have already defined that small p. We need to find this probability p, which says that the probability that he drives to work. All right. We also know from above that the probability of Chin being on time, that is 0.86, right? The mention over here. Now utilizing this information and the probability of being on time. So if we have a look at this tree diagram, Chin can be on time at office when he drives or when he takes a train based on their respective probabilities, obviously. So these are the two events or two respective occurrences when Chin can be on time at office. So we can say that probability of on time would be equal probability of drive, that is the event when Chin drives, intersection on time plus the probability of train intersection on time, which are, by the ways, these two respective branches, right? So for the first part, which is the probability of drive intersection on time, this is equal to 0.7 p, the product of 0.7 and the probability p, plus for the second part, the probability of train intersection on time, this is equal to 0.9 multiplied by 1 minus p, and this all is equal to 0.86. So we can solve this equation for p, and if we can simplify it a little bit, 0.86 is equal to 0.7 p plus 0.9 minus 0.9 p, and we can simplify it to um, 0.86 minus 0.9 is minus 0.04 equals minus 0.2 p, and the minus sign to cancel out, and p is equal to 0.2. So the probability that he drives to work is 0.2, which we have defined above as this small p. All right. So if we can say that probability that he drives to work is 0.2, that the probability that he takes train is obviously 0.8 or 1 minus p. Moving on to the last part of the question. Given that he is late for work, what is the probability that he took the train to work? All right, so we have to find the probability of Chen taking train for work, given that he is late for work. All right, so let me scroll a little bit above so that we can see the tree diagram. So this is probability of train given that he's late for work. So by definition, this is equal to probability of train intersection late over probability of late. So the denominator is known to us because the probability of on time is 0.86, which is given in the question. So probability of late would be 1 minus 0.86, so 0.14. As far as the numerator is concerned, if we go back to our tree diagram here, so the probability of train intersection late is this branch over here, right? In fact, let me choose a different color so we can distinguish it. This is this branch over here. So this is basically the case when Chen takes a train and is late for work. So let's solve it. So the numerator would be 0.1 multiplied by 1 minus p. P was 0.2, so that is 0.8. As far as the denominator is concerned, that was 1 minus 0.86, so 0.14. So solving it real quick. So the answer is 0.57. So this is a probability that Chen takes a train to work, given that he was late for work, right? So that's it. I hope this session was fruitful. We solved almost all the questions related to different aspects of conditional probability. See you in the next session. Thank you.